starting the lecture now. I see that quite a lot of you is not participating in the lectures. Okay, that's your decisions. Okay, so for today, I don't have anything, any introduction. We were in the middle of presentation concerning synchronization, so we'll move on to that. Sorry, I need to share the screen. Okay, so the last thing I was talking about in the previous week, I think, was about semaphores. If I am mistaken, please correct me. But I think that was the last thing I managed to talk about during our meeting last week. Am I correct? Okay. So you remember now that the semaphore is a mechanism. In practice, it's a system function which you can use either directly or inside some other library when you are developing your program, and it allows you to suspend a program, move it into the sleep state if a condition is met, and awaken it if another process executes the V operation, that means awaken operation, and then the process which was waiting is moved from the sleep state to the ready state, and when it gets the processor, it gets executed. Okay, the important thing about the P and V operations is that during the execution, they are executing by the operating system kernel, which means that they will not be switched between processes otherwise than when you cause them to do it. So you have the operating system has the control about switching the processes. So there are no race conditions which can cause that either you lock your synchronization or arrive at the race condition where you don't know what will happen. Okay, I have also told you that there is a very special implementation of semaphores that you might get into contact with. That's the spin locks. The spin locks were developed for multiprocessor, actually for a large number of processors available in an executable environment. In those situations, as I have said, it's not necessarily a good idea to make the process sleep. Sometimes it's better to use a busy wait, or in Polish, it's called hot loop. So you can use either term, but which wastes the processor time. But in case of vastly multiprocessor environments, this waste is not significant, and putting a process to sleep and then awakening it is consuming processor time, and also, what is more important, is causing delays during processing. So In such environments, there is a special implementations of semaphores, which are called spin locks, which use busy waits. Otherwise, you don't have busy waits, and when you are designing your own programs, you always need to look in the code whether you are not using busy waits, because that's considered as a quite serious error in multi-process or multi-thread programming. Okay, so if we understand this, we can, I can also remind you that the critical section problem, which I have discussed and shown you software solutions to it, can be very easily and very efficiently solved using these semaphore mechanisms. Okay, you can solve them using binary semaphores. You can solve them using the general the counting semaphores. I will show you here the solution on the most basic counting semaphores. Okay, so the semaphore is initialized to 1 when a process wants to enter the critical section. Then it performs the P operation, which means that it tries to decrease the value of the semaphore. If the semaphore is in value 1, it will manage to do that and will directly go into the critical section. Okay? When it leaves the critical section, it will perform the V operation, increasing the semaphore back to 1. Okay, so while it is in the critical section, the semaphore value is 0. If another process, I don't know which, it's completely random and unpredictable which one will reach the critical section first. So the thing which is the first, which is the second is completely arbitrary. So if the second process reaches the critical section and the first is still in the section, the S will be 0. So the P operation will cause the process to sleep. Okay, the process will not be able to enter the critical section, but when this process leaves it, then it will awaken and then it will get into the critical section. Okay, so this solves both the problem of mutual exclusion and the problem of progress. And as I have said, the problem of bounded waiting is actually a problem which cannot be solved this easily. In case of 2 processes, it just means that you should not write the programs in such a way that they stay in the critical section for long periods of time. So most of the time, the processes should not be in the critical section, and then you don't have the problem of bounded wait. In case of multiple processes, this might be a problem, and there are some specific ways to approach them, but that is not part of this lecture because it's much more advanced. Okay, you might be studying it in some other lectures. I don't really know because I don't know your program too well. Okay, another problem, which is also a very common problem considered in computing how to write a program, is a problem which is called the bounded buffer problem. Okay, a bounded buffer problem is a problem where there are 2 processes. One is producing something and putting it in the buffer, and another is a process which consumes. So it's often called the producer-consumer problem. because there is a producer which must produce some data, puts it into a buffer, and then there is another process which needs to consume, that means access the data produced by the producer, remove it from the buffer, and make use of it. Okay, so if you think about it, it is something similar to what you have with pipelining, and actually semaphores and mechanisms, synchronization mechanisms are used to implement pipelining in a similar way that what I am talking about the bounded buffer problem. So one process needs to add something to buffer. The second process needs to something remove from the buffer. The problem is that if the first process hasn't input anything to the buffer, the second process has to wait. It has to wait until the first process puts something to the buffer. Okay. Again, if the first process produces a number of different results and puts it in a buffer, then and the second one doesn't consume those data, doesn't read them, then after some time the buffer will become full. So what happens then? If the buffer is full, the first process, the producer process, has to check whether has to wait until the second process catches up and takes data from the buffer. Okay, it's actually a very common programming problem. So it has a standard library solution, but this solution can be achieved using semaphores also to get full synchronization. So for this problem, the standard solution uses 3 semaphores. Okay, one semaphore is for suspending the producer process when the buffer is full. So initially, this semaphore, I have called it empty. So initially, it is set to the maximum value of the buffer. Okay, and each P, when you are entering this, the producer is entering the data, decreases the value by 1. At certain point, if the consumer doesn't catch up, at certain point it will end up being 0. That means being empty. And if that happens, then the P operation on the semaphore will suspend, put to sleep the first process. Okay, then inside this we have a standard critical section, because operations on a buffer, on any structure similar to a buffer, it's a critical section. So we have a second semaphore which ensures that the operations are not being done both by the 2 processes at the same time. So this is a standard critical section mechanism. And then we have another operation B, but on the other third semaphore, which is initially 0. This semaphore indicates how many pieces of data are already in the buffer. Initially, they are 0. When they reach n. Okay, they will reach n only when they will never reach n, because empty will not allow that to happen, but they will increase when the data is entered into the buffer. Okay, the second process tests the value of the full semaphore. So if the full semaphore is 0, the second process will be put to sleep on this P operation. Okay? That means that at this point we are certain that we move on only if something is in the buffer. Then we have the critical section in which we remove pieces from the buffer. The critical section is necessary because the buffer might not be at the same time, it might not be empty and it might not be full, which means that both processes might traverse the first P operation, and then one of them will have to wait for the other to complete before entering the critical section. At the end, the V operation increases the size, the value in the empty semaphore. Okay, that means that it's if the first was waiting for the semaphore to become empty, to have an empty slot, then this process will awaken and can add the data to the buffer. Okay, so this is a simple problem, but you see that even such a simple problem has quite a number of synchronization issues that you need to solve. You need to solve the critical section problem when you add remove, but you must also solve the problem of not waiting in a busy wait but sleeping if the buffer is full or if the buffer is completely empty, okay, depending on which process. Okay, so I hope this is clear, that you understand what happens. And now we'll move on to something more connected with the laboratory. That means to the synchronization mechanisms that are available in pthreads. Okay? In pthreads, the most important mechanism is something which is called a mutex. A mutex is a very lightweight implementation of semaphore. A mutex uses puts threads to sleep, similar to processes like semaphore, but the whole problem is that its implementation is very simplistic, and because of that, there is one very strong limitation. Okay, mutex locks and mutex unlock. There are two operations. They are similar to PV, but mutex is binary. So that means it can be either locked or unlocked. There are just two states it can be in. So you can lock a mutex which is unlocked, and you can unlock a mutex which is locked. Okay, you should never try unlocking a mutex which is not locked. That's an error, programming error, really. Of course, you can try to lock a mutex when it is already locked. That means that the second thread which tries it will be put to sleep until the first thread unlocks the mutex. So there is one limitation that unlocking should not, unlike binary semaphores, does not put a thread into sleep, but is an error simply, which you can ignore, but it's still an error. Okay. Whereas when you lock, of course, it behaves as similar to a binary semaphore. Okay, so there is another second limitation to mutex. This limitation states that if a thread locks a mutex, the same thread must unlock it. This is a very important limitation. This simplifies significantly the implementation of mutexes, and that's why it was introduced, that mutex lock and unlock can be performed much quicker than semaphore PNV operations. Okay, and that this limitation does not cause any problem. So to solve the critical section problem, which is the most common problem in programming, you don't need anything else. A mutex will be just enough. Okay, at the entry you lock the mutex. At the when you exit, you unlock the mutex in all the processes, and then the critical section will be accessed only by one thread or one process at a time. Okay? So that's one thing about mutexes. So since they are a much simpler implementation than the operating system's mechanism, which is called the semaphore, they are the preferred way to do critical section protection when you have a multi-thread program using Petrets. Another, but if you look at the other problem that I have discussed, the bounded buffer problem, you see that this this sync semaphore can be used directly. The empty and full semaphores, okay, there are two problems really. That the mutex is not binary, which is that the mutex is binary, and here you need something which is not binary. But you are not, that is not really a problem, because you can use a simple variable to overcome it. Yeah, of course, kept inside the, so the code would be slightly more complex, but you could do it just as well using a mutex. But there is another problem, and this is not possible to overcome. And this problem is that in case of this mechanism, the semaphore empty and full, the operation complementary to putting the process the thread to sleep is called by a different thread. This is not allowed in case of mutexes. For that purpose, in the Petrets library, another mechanism was introduced. Okay? This mechanism is called a conditional variable. And on this mechanism, two operations are again defined. One is the conditional wait, and the other is conditional signal. there is a third operation, a third possibility, pet-thread conditional broadcast. Actually, it's really very simple, very similar, the conditional signal and conditional broadcast. One wakes a single thread. If you don't want to control in any way which of the waiting threads are to be awakened, you call the conditional signal. The conditional broadcast wakes all the threads waiting on the conditional variable, which means that they all wake up and they compete which one will be running. Still only one will enter the critical section, but you can, using additional variables, you can control which one. So both solutions, of course, are all right, depending what you need. The conditional wait and signal are called by different processes. That means one thread is calling wait, at that time it suspense, and then another thread must send the signal to wake it up. And you see that if you look at the bounded buffer problem, you will see that this addresses the problem of the empty and full semaphores. Instead of them, you need you will need two conditional variables, and you will achieve the same problem. Okay, the implementation of conditional variables also have some limitation. The whole point is that the pet-thread conditional wait must be called from within a critical section. So you must have a critical section defined using mutex lock and mutex unlock, and inside the critical section you call the conditional wait. Okay, so a thread enters a critical sections. Inside it calls the wait operation. That means the thread is, while it is inside the critical section, it is put to sleep, even though it's inside the critical section. Okay, but when it is put to sleep on conditional wait, at the same time the critical section is released. That means even though the process have not performed a mutex unlock, when this variable is puts that thread to sleep, other threads can enter that critical section. So they will perform the mutex lock even though you have performed it earlier. Okay, so the conditional wait releases the critical section, but it releases it only for some time. Okay, once the thread which was sleeping on a conditional variable wakes up, it again takes hold of the critical section, so other threads cannot enter this critical section. For this reason, conditional signal and conditional broadcast should also be called from within the same critical section, because if that doesn't happen, you don't. There is a slight race condition, which is not very important. So a lot of programs actually ignore it, but the documentation says that it has to be done. In case of C++, where you are using the threads, and there is also the conditional variable in there because it's the same library, the situation is such that you don't need to put the signal and the broadcast inside a critical section because it's done internally. So when you call a conditional signal, inside that code is the mutex lock unlock performed anyway. So there is no race condition because it's eliminated by the implementation of these functions. So you can call them also outside critical sections, but you can call them inside. If you call signal from within the critical section, you know that wait will become effective only when the critical section that was signal was in is left by the thread which was doing the signal. Okay, it's a bit complicated. You will have the last laboratory, you will be using conditional variables. During the today's laboratory, you will not. Next weeks, for those of you who are doing on Tuesday the laboratory, you will be using mutex locks. The Friday group has already moved past, and there were some problems that you had problems and finishing on time. But I hope that the other groups, since I have made this introduction in advance, will not have this problem. Okay, so these are the mechanisms for synchronization which are available in pthreads. There is one thing. If you look into any programming language, you will have implementations using semaphores. You will have that means a library for semaphores. You will have the pthreads library or thread library in case of C++. You might have some other mechanisms I will be speaking about in a moment, like communication queues. There is one thing which is very important, that if you are using processes and operating system mechanisms, you don't need to worry about compatibility between mechanisms. But if you are using libraries like pthreads and others, you should avoid mixing different mechanisms. So if you are using threads, you should avoid using semaphores. Actually, on Linux, you will not run into problems, but if you try to move the same program to other operating systems, like older Unixes or some or MacOSes or whatever, you should expect problems when you have mixed different libraries. So if you decide to use pthreads, you should use the mechanisms defined in pthreads instead of the other libraries. Otherwise, you might run into conflicts, because there is an obvious conflict if you think about threads which are not system threads. Okay, in Linux, all the threads actually are system threads, and because of that, the operating system allows mixing of those mechanisms. But if you have a user space threads instead of system space threads. I spoke about that last week, so I hope that you remember what's the difference. Then you might end up using a mechanism which is specific for processes, and you will hang on the mechanism not just a single thread, but the whole process. And that does happen when you use, for example, semaphore library on some Unixes. If you use semaphore libraries from a multi-thread program using pthreads. So you must be careful about that. The fact that something is done by one library doesn't mean that it is compatible with what is done, being done in a different library. It's not a problem specific to threads. In all programming, if you are mixing libraries, you must worry about the compatibility between them. Okay. Another thing that I wanted to tell you about is something which is called inter-process communication. Actually, inter-process communication and inter-process synchronization, or inter-thread communication, inter-thread synchronization, they are the same problems, but there are mechanisms which are specific for one and mechanisms specific for communication and others for synchronization. Of course, if you don't have a synchronization mechanism handy, but you have communication mechanism, you can use communication mechanisms for synchronization, because if you have implemented communication where messages are sent synchronously between two processes or two threads, then you can use that for synchronization. Not necessarily the best idea, but sometimes it is better than mixing different libraries, as I've said. And also the other way around, if you don't have communication mechanism, but you have semaphores or mutexes and variables, you can implement using them also inter-process communication. Okay, inter-process communication assumes, in case of processes have separate memory images. That means that there must be a mechanism to sending data from one to the other. In case of threads, since they are in the same memory, you don't have that problem, but you have the problem of synchronizing the exchange of data between the threads. So if you need to send and receive data, instead you can use the communication mechanism. A communication mechanism sends some data by means of an intermediate buffer from one process or one thread to another process which receives it. Okay, so the first problem is the addressing problem. Okay, if you want to send a message from one process to another, you need to tell which process needs to receive it. So direct addressing means that that the address you use is the address of the sending and receiving processes. Okay, processes have their process IDs, they are numbers. So you could use that, but that wouldn't be very convenient, especially since you cannot predict what will be the ID of each process, because that depends on dynamic situation in the system. So direct addressing is actually of very limited applicability. So instead of that, for inter-process communication, a different approach was introduced, the approach of using something which is called communication channels. Okay, if you have a communication channel, then you are sending a message to the channel, and another process is reading the message from the channel. You see, it's very similar to the problem of bounded buffer. That's why I said that the two mechanisms, the synchronization and communication, are really very similar and they are complementary. So if you send a message to the buffer, you use one operation, the send. You need to state the name, or it's always not convenient to use the names inside the program. So instead of using the name, you will usually open a channel and then you get the handle to the channel and you send a message to the channel. And in the receiving process, you call a different function. Again, on an opened channel, you call receive. And of course, here the argument is a message, and here it's a memory area where the message should be written to. That means you provide a message address. Okay, there are three different implementations how this mechanism can be used. So you will find in a lot of operating systems, libraries which will be providing you inter-process channels and communication between the channels at the operating system level or at a library level. So you can use them. The problem really is with internal implementation, because the message is being set to a buffer and another process is reading from the buffer. Okay, so in between there is a buffer connected with the named communication channels. If there is a buffer, this buffer can be different in size. Okay, the buffer might be limited to 0 buffering. Okay, and such mechanism, such implementation of communication is often called rendezvous mechanism. It means that if one process is sending, there must be another process receiving, and if a process tries to send and there is no process waiting to receive, then it will hang. It will wait until a different process called receive. Then the send and the receive will be performed at the same time. In this situation, you don't need any buffering. That's why it's called 0 buffering, because the operating system from the send process knows what message is to be sent, from the receiving message where it is to be copied to, and the operating system can directly copy from the address space of send to the address space of receive, copy the message directly without any buffer. Okay, the consequence of this is that if you call send but receive, there is no process waiting to receive, the sending process is hung. If you call receive but there is no sending process waiting to send, then the receive process will have to wait, will be put to sleep, and only when there is both one sending and one receiving, the operations will be done. Okay, so this is one of the communication mechanisms. very simple, and you see it's actually very symmetrical, because both the sending process and the receiving process can be put to sleep because of calling the communication mechanisms. Okay, a very different situation is in something which is called unlimited buffering. In this case, the send operation always is always performed without waiting for the for any process to receive data. Okay, so the data is put into a buffer, and the send operation ends directly. So you can go on to do something else. The send operation will never put your process to sleep. Okay, the receive operation will operate differently, because if there is no data in the message queue, in the channel, then the receive operation will put the process which calls receive to sleep. If there is data ready to read, then the receive will be performed either directly or after waiting that a process sends and something is there available. Okay, the name unlimited buffering is a bit misleading, so I need to comment on that, because of course buffering means memory. You never have unlimited memory. You might have a very large amount of memory, you might have smaller amount of memory, but never unlimited. So unlimited buffering is something which is contradictory by itself. Okay, in real implementation, it simply means that the send operation is never put to sleep. If the send operation tries to put a message in the communication channel, but the communication channel is already filled up, then the send operation will return an error to the sending process. So it will not put to sleep. It will just return, but will not perform putting of data into the channel and will return an error. Okay. So an implementation in between the two, zero buffering and unlimited buffering, is something which is called limited buffering. Limited buffering means that there is a declared size of the buffer. When you create the communication channel, you declare how much memory it should use for buffering, and the send operation behaves similar to the unlimited buffering situation, but if the buffer is already filled up, it will then be put to sleep. So in this case, of course, the receive behaves exactly the same as in case of unlimited buffering. If there is data to be read, it reads it. If there is no data to read, it waits. It puts the process is put to sleep waiting for it. Okay. So you see, those are the different mechanisms that you can meet in, when you are programming in actually any language, especially in C or C++. But if you are using other language, you will also be able to meet all those problems and all those mechanisms. Maybe not directly, they might be hidden inside some higher level programming constructions, but they are there. Okay, so this is what I wanted to tell you about synchronization. And if you don't have any questions, I will move on to the next set of slides, to the next topic that I have to cover. And the next topic is memory management. So I will just, I have now switched to the next slide, the memory management. Okay, so memory management means I have already mentioned a lot of time really discussing the processes, discussing the resource that a program to run needs to be in memory. It needs also memory to keeping data when it's performing. So that means it needs memory for all its variables, whatever type of variables you are using. So this way, each process must have its own memory image. And I have said that memory is a resource, which means that in case of multi-thread programming, all the threads from the same process will share the same memory. So memory management is process specific, not thread specific, but otherwise it's exactly the same thing. Okay, so if we move on, the first thing is how the memory is defined, built. So that is something which is not done by the operating system, that's done earlier on. When you compile a program, you are building something which is called an executable. An executable is a representation of the program's memory inside a file. When you load it from using that executable, if you load that into memory, then you produce the core image of a process. A core image of a process is exactly the same thing as a process context. The user context of a process and core image is actually the same thing, only the two terms are used depending whether we are talking about memory program loading and program executing. And so in case of program executing, the context is changing. That usually means that the core image is changing during the processing. Okay. Before I go into more details, I need to make a strong distinction. You must distinguish between compiled languages like C, C++, Pascal, and interpreted programs like Java, like Python. Okay, actually, interpreted programs, when you have the program, it is not executed by the processor. There is another program in case of Java. That's the situation that you are most familiar with due to the lectures of Dr. Walkowiak. So if you have Java, the Java is being executed by the virtual machine, Java virtual machine. Okay, this Java virtual machine is a program written in some language, compiled. It's a program that I am talking about. So if so it's an executable program, but in this sense, Java is not a program. It is data for the Java virtual machine to be running. Okay, from the operating system's point of view, a Java program is not a process, okay, because the process will be the virtual machine which will be running that Java program. Okay, but what I am saying is that first you need to have a program. A program you write in source code, in C, in C++, and that way you get source program modules. You compile the modules, and then you get object modules, which you can combine together to produce the executable. Instead of combining them, you can remember a pre-compiled module, and that is what the static libraries are about. Okay, actually, a library is a collection of object modules which were pre-compiled and packaged into a single file, which is called a library file. So when you are compiling a program, you produce object modules. And you can, and the programming languages are so organized that when you have more than one file, that means more than one source module, they should compile completely and independently. Okay, because they compile independently, you can put them in the library, and you will be then able to use them, even though you don't compile them at the moment when you need to produce the executable. Once you have produced and you have your own object modules and libraries, you start a process which is called linking. Linking means you combine the modules into a single file, and you produce a file which is called executable. In case of Windows, executable almost always has the .exe file name extension. In case of Linux, actually that doesn't apply because Linux identifies files not by means of extension, but by means of the content, which means that that a file extension doesn't really mean anything. It is just part of the name. Okay, so once you have the executable, you are ready to run a program. Okay, so you load the program into memory, and once you have loaded it, it starts to execute. Okay, there are a few problems which you need to solve. Okay, if you have a source program which is in more than one file, then you have a problem of which memory addresses correspond to what variables, whether variable names can be reused in different modules, or they are just local. All the names which are local cannot be used by other modules. Names which are global, they can be used by other modules. When you are dealing with C or C++, this is not necessarily the case in other languages, because different high-level languages solve this problem differently. But in case of C, C++, the global variables, their definitions, you include in the .h or .hpp in case of C++ files. Okay, those files, they are just a means of telling the compiler that some names are global of a specific type, but they are defined in a different module. Okay, so during the compilation, you compile each file separately, and each file produces a separate object module. You can compile them in any order you want, and the object modules will still remain exactly the same because they don't depend one on the other, except for the naming conventions. Okay, so when you produce the object module, that object module is always accompanied by a list of names which are defined inside the module and which are connected with specific memory addresses inside the module. Okay, so for example, if you defined a function in C, the name of the function, all the names of function in C are global, which means they are reusable in other modules. So you have a list of all the file names, also of all global variables that you have defined. Global means static, defined outside any function. Okay, in the case of C and C++, but not necessarily in case of other languages. Okay, so those names are listed, and addresses inside modules, where is the code corresponding. If they are functions, that means there will be code corresponding to them. If they are variables, in what area of memory which will be allocated later to the modules, each variable is placed in. Okay. Besides that, this is one table which is inside each object module. There is also another different table of external symbols. If you have a definition of a function in an .h file, but you don't have the code, what the function really does, just the declaration that there is such a function in some other module, then this file function name will appear as an external symbol. An external symbol is always associated with the code of the module, where in the module this function is being invoked. So there is one table with definition of global symbols, and another table with invocations where the module refers to a specific name. Of course, module never refers to name. It refers to an address and needs that address, but the address is not available because it's in a different module. So in that case, this place where this address should be put will be connected with the external symbol. Okay, and I have said there are that static libraries are exactly like object modules, except they are packaged many objects are packaged as a collection inside the same library. Okay, so then a process of linking takes place. Okay, during the linking, the global symbols and the external symbols of different modules are matched. Okay, so if in one module you have a global symbol which says, for example, function sin, and another you have a table external symbol sin, then the two are matched and treated as the same. If there are two global symbols with the same names, the first name will be visible as a global symbol, and the others will be ignored. If there are oh, sorry, no, I'm actually, no, if there are multiple symbols with the same name in object modules, there will be a conflict and you will get an error message during linking. In case of libraries, it's a bit different. I will be talking about that in a moment. If there is an external symbol and inside and none of the object modules and static libraries, there is any global symbol of the same name, you again get a linking error which states that some name is not defined. It is used but never defined. And it is possible to achieve that, and it's an error really. Okay, once you have compiled an executable, you load that into memory. I will be talking about that in a moment, so that the program can be executed, because the real program always executes from memory, not from disk, not from other types of storage, but must be inside memory. Okay, to run. So I have already spoken about global and external symbols. I should speak a little bit about what happens with the different types. So if you have a label for a jump instruction, that is an address which is not an address, a numerical address which is understandable by the processor, but you have a name. So this is a type of variable, but not referring to addresses for storing some values, but a variable which indicates some place inside your code. So this might be a global symbol if it is defined as global, or it might be a local symbol if it is not to be reused by in other modules. Okay, when we speak about variable names, it's a bit more difficult, because in any language there are two types of variables: static and dynamic. Static variables are inside memory, which is allocated all the time in the program. Okay, so in case of C, also in C++, this will be declaration of variables which are not inside any function or any class. Okay? Such a variable will have allocated memory all the time during program running. If you have variables defined inside a function or inside a method, those variables are dynamic. The memory is allocated when you open the function, and the memory is released when you close the function. So if the same function is called twice, it might, the variables will be in completely different places in memory. So those variables are never global, whereas static variables can be global and can be external in other modules. And then you have function names. They are again in C or C++ always global, which means that always static, because the code of the function has a specific place where it is kept all the time. In case of methods, in class methods, it's a little more complicated, because that depends how the method, how the class is being done, because some methods will be static methods, and then they of course have memory. They will never be global variables by themselves, because they are addressable through the static class declaration, but they will be static, others will be dynamic. So it all depends, okay? Another thing is that each module defines a few segments in memory. That means when you compile the module, everything which is statically declared must be allocated place inside the segment. This segment is still something virtual, because it will be in memory only when it is loaded, but you have to say that function A is from memory 3000 to 3010 or something, and so on. In case of segments, you don't know whether it will be 3000, but you know that it will start at a certain address from the beginning of the segment, and it will take certain space inside the segment. So a segment has its size. When you load it into memory, all the displacements representing that inside the segment are transferred to absolute addresses. But that's done during loading, not during compilation, and nowadays also not during linking. That's done during loading of a program. So each global symbol will be, as I have said, there are each module is compiled into a few segments. In fact, I don't know whether in all the operating systems, but in Linux, in Windows, they will be compiled usually into 4. Am I right? Yes, I think 4 segments. The code segments, that's where all your functions, when they are compiled, they are put in. There will be a second segment, which is called, which is static variables, initialized variables. Initialize static variables. When you define a variable and you define its initial value, it is an initialized static variable. If you defined a static variable, but you don't define its value, afterwards you can have you can set the value of such a variable to a specific value. And in both cases, you can change it. But in case of uninitialized variables, they are put into a different segment from the initialized variables. The reason is very simple, because in case of uninitialized segments, you don't need to remember in exec the segment as it stands. You just need to remember what is its size. In case of static initialized variables, you need to remember inside the executable what is the initial value of those variables. So those are the three segments, and I have said there is a fourth. The fourth is the stack of your program. So when your program is running, it puts return addresses of functions onto the stack. Also, all the arguments of functions, they are put onto the stack. And when you leave the function, they are removed from the stack. And also all local variables which you define inside function in C or in case of C++, that's also true for the methods. They are placed on the stack. That for that reason, there is a separate stack segment which is never initialized, similar to uninitialized static variables. But unlike initialized static variables, the compiler cannot compute what will be the necessary size of the stack. That is something you need to define when you create your program, or you must assume that the size of stack, which is default size when you don't set it to anything else, will be enough for your program. Okay, why can't you predict what is the size, what is the necessary size of the stack? That's very simple. The problem is that recurrency, also library functions, you can't predict how much stack they will use, how many recursive calls inside such a module will take place, and then you don't know also how much stack you need. Okay, so this is what is being produced during compilation and what is used during linking to resolve problems. Okay, if you compile a multi-module program, you on the command line for the linker. Actually, if you call the compiler, it internally calls also the linker in the case of GCC, or you can stop the compiler from doing it, and then you need to have a make file which first compiles the program and then links the program. Okay, so if you have multiple modules, you first have to separately compile each module. Then for the linker, you provide the name of all the object modules which are to be combined, and you also provide the libraries that are to be used. So the first thing about it is that the object modules which you provide are combined together. What does it mean they are combined? It means that the global symbol tables is matched with the external symbols tables. Okay, each module has a global symbols table and external symbols table. So starting off with one module, you get add all the global symbols from that module into a global symbol. Then you analyze the external symbols if they are matched, then the matching is performed. So all the global objects are matched. Some external symbols will still be unmatched. And for those external symbols, you look into the libraries. Okay, so the object modules are combined at one go, all the global tables into one, all the external tables into the second. If there are more than one global of the same name, then you get an error and the matching will break down. But if not, then we continue. All the external symbols which have the definition in the global symbol are satisfied, the modules are appropriately combined one with the other, and those external symbols just disappear. They are removed from the external symbols table. When that ends, then the global symbols table cannot satisfy some external symbols. The linker starts to analyze libraries one at a time. It opens the first library called on the command line of the linker. It reads the first module, gets the global and external symbols from that. If any of the global symbol matches an external symbol which is already left from linking the object modules, then this whole module is extracted from the library and added to your program. And also its global symbols are added to the global symbols table. Its external symbols are added to the external symbols table. Okay, so adding this new module will satisfy some external symbols which we had, but it might also add some new external symbols. And this is a big problem with linking, in linking, that if you use a name of a function which corresponds to some library name, then this name will be taken and the external symbol will be just removed from the table. So even if you don't want to do it, so you can break a library if you use names which are the same as library names used internally. To prevent it, there are some conventions, but there are just conventions. So if you are not careful, that might happen. Library functions usually have, if you are not supposed to use them, they have strange names with double underscores at the beginning and things even stranger, just to prevent you from using the same name in your program. But if you are unlucky and use such a symbol, then during the linking, you will substitute some function that the library function requires by your own function, which might break things up. Okay, but if that doesn't happen, you go on from one library module to the other until you analyze the whole library, or until the external symbols table becomes empty. If the external symbols table becomes empty, you stop analyzing libraries because all the external symbols have been satisfied, and that's it. Okay. If not, then you go to the second library and so on. If a library is incorrectly organized, which should never happen, you might it might turn out that you need to include the same library more than once, because each library, when the modules are being added, is just analyzed once. So if in a library there is from one module there is an invocation to an earlier module, it will not be satisfied. But that's something which is, it doesn't happen with distribution libraries. It might happen when you get some strange library from some very questionable source. Okay, so this way your program becomes an executable in an, okay. It tells me that I need to finish my lecture in a moment. So, so just to finish this slide, in this way, you add from static libraries, object modules, and your executable file grows. In fact, when you are using static libraries, then the executables can become very large. And that's not because your code compiles to large number of machine code. It's because you have included a number of different library modules. The worst possible situation is if you are using graphical libraries, because if you are using a graphical library, there is a very strong dependency between the functions in the graphical functions. If you use a window, inside the window you have different decorations. So even though you don't want to have code for minimizing windows, for maximizing windows, for closing windows, you will still, the library will still add default functions for all of that and so on. So when you are using static libraries, especially such large libraries which are strongly knit together, then the executable can become very large. To prevent that, another approach was developed, which is called dynamic libraries. But about dynamic or shareable libraries, I will be talking next week, because I have run out of time now. So I will be anyway starting from this slide. So for today, that's all that I wanted to present you. If you have any questions, then I will be happy to answer them. If you don't have questions, then we'll be meeting actually in 5 minutes, I am afraid, to continue to talk about the about the library. Sorry. Oh yes. We will be talking about the laboratory. Okay. So thank you for now, and see you, some of you in 5 minutes, some of you in some time later. So thank you. Bye-bye.